and gentlemen, this is section 6.1, and we're talking about ratios, proportions, and the geometric mean. Well, ratios, we're not going to talk too much about them on their own in this section. We did those some practice review of ratios for warm-ups. If you want more practice or for more videos, you can go to khanacademy.org. And they have plenty of tutoring videos if you want an extra review with ratios. They also have practice problems that you can get step through when you're working with them. This link is also on your Edline page under links. But let's start with this problem. You're planning to paint a mural on a rectangular wall. Rectangles are nice to work with, so that's great. You know that the perimeter of the wall is 484 feet, so we know that. That's important. And that the ratio of its length to its width is 9:2. Find the area of the wall. Well, to find the area, we know we need to take the length times the width. So you might be tempted to take 9 times 2 and get 18 for the area, but that's incorrect, because if you check the perimeter by adding all of these sides together, you don't end up with 484. If you add 9 and 2, 9 and 2, you end up with 22, which is not the perimeter you wanted. The reason why this is the case is because the ratio of 9:2 is reduced. It's not the original ratio of the actual length to the actual width. To unreduce this, you can multiply the numerator and denominator by some number. So let's say we multiply both of them times 2. We'll end up with 18/4. It still reduces to 9/2, so our length could be 18 and our width could be 4. But if we add 18 and 4, 18 and 4, we still don't end up with 484, so that's not going to work. Let's try multiplying by 2 again. 36/8. But if we add 36 and 8, 36 and 8, one second, we still don't end up with 484. So there's a lot of guessing and checking if we do it this way. There's a much easier way we can do this. Instead of guessing and checking what I should multiply by, I'll say if I multiply 9 and 2 by a factor of x, that should get me back to my original ratio. So really this is 9x over 2x. I can solve for x and then plug it back in to find my original length and my original width. Well, to do that, my perimeter is 484. And that equals 2 times the length plus 2 times the width, way back in chapter 1. Well, if I call my length 9x and my width 2x, this is 2 times 9x plus 2 times 2x. From here, I can combine like terms and multiply and end up solving for x. So if I do that, 2 times 9 is 18x. 2 times 2 is 4x. If I combine like terms, I end up with 22x. And then from here, if I divide both sides of my equation by 22, I end up with x actually equaling 22. So there's my x. So to solve for my original length and my original width, I'm going to plug x back in. Well, 9 times 22 will give me my original length. 2 times 22 will give me my original width. So in this case, if I multiply 9 times 22, I end up with 198 for my length and 44 for my width. And you can check this. If we add all of our sides together, so we put our answers over here, we know that this is 198, 198, 44, and 44. If you add all these values together, you do end up with 484. So your answer will check. And this fraction does reduce to 9/2. These are just our original numbers, so that's how we unreduce it. But for this problem, we're not asked for the length and the width, we're actually asked for the area. So to find the area, we're going to multiply 198, my length, times 44, my width. So we're going to get a very large value. If we multiply these, we end up with 8,712. And since we're talking about feet, that's our units, and since it's area, that's feet squared. Kind of a long process for a problem like this. We'll do a few more examples just to kind of make sure we're more comfortable with it. Usually we'll be dealing with triangles, so let's do a triangle problem with this. Let's say we have a triangle, and the problem states that the measures of the angles in triangle CDE are in the extended ratio, extended because we have more than two values here. The extended ratio 1 to 2 to 3. Find the measures of the angles. Well, we know our actual angles aren't 1, 2, and 3 because all the angles inside a triangle should add to 180. But 1 plus 2 plus 3 gives us 6, which is obviously not 180. So this is reduced. We want to unreduce it. I should put that there earlier. So to unreduce it, we'll attach an x to each one to find out what number all of these should be multiplied to get back to our original. And you can see that labeled in the picture over here. Instead of 1, 2, and 3, we have 1x, 2x, and 3x. And if we combine like terms, we end up with 6x equals 180. And dividing by 6, we find out that those terms should be multiplied by a factor of 30. So to find your original angles, you have one of them is 30. One of them is 2 times 30, which is 60. One of them is 3 times 30, which is 90. So your angles are 30, 60, and 90. And if you check, you can add these and they will end up equaling 180, so your answer checks out. So again, you always attach an x number, or x variable, to each of your numbers in your ratio to unreduce it. Let's do one more like that. Not number 3, let's do number 4. A triangle's angle measures are in the extended ratio of 1 to 3 to 5. Find the measures of the angles. Well, we know that 1, 3, and 5 don't add to give us 180, so this is reduced. So we'll say 1x to 3x to 5x. And for our equation, that should be 1x plus 3x plus 5x, and it should equal 180 because all the interior angles of a triangle always add to 180. Combining like terms, 9x equals 180, so x is 20. And when you plug 20 back in over here, 1 times 20 is 20, 3 times 20 is 60, 5 times 20 is 100, and if you add those, they do end up to 180, so that is the correct answer. So here's an example of how you can go back and find your original values. Let's do some examples with some proportions instead of extended ratios. Just a few quick examples. These should be very familiar. We'll do 2 of them, just 5 and 6. We won't worry about number 7. So for number 5, to solve a proportion, we need to cross multiply. So we'll multiply 5 times x and set it equal to 2 times 8, which is 16. Divide both sides by 5, we end up with a fraction of 16/5, or you can write it as a decimal. Either way is fine. So that one's nice and quick and easy. Our second one, not so much. If we cross multiply x minus 3 times 4, you make sure your x minus 3, that expression, always stays in parentheses. So if you ever have an expression like x plus something, x minus something, always keep it inside parentheses. And let me go ahead and, just for emphasis, make sure I put that in there. Multiplying the other direction, 1 times 3x is simply 3x. So there's our equation that we can solve. You need to keep those parentheses here because eventually you will distribute. So this is 4x minus 12. The issue that many students run into is not using parentheses, so they end up with 4x, not a 12. They end up keeping the 3, so that's a problem. If we subtract 4x from both sides, you end up with negative 12 equals negative 1x. And divide both sides by negative 1, so positive 12 equals x. So the big thing with proportions is when you cross multiply, keep any expressions in parentheses. So anytime you have a variable and you're adding or subtracting something, keep it in parentheses. The last little bit for this video is the geometric mean. This is the key concept definition in the textbook. It's kind of a long drawn-out process. I'm just going to talk about the mechanics since this is just a review video. To take the geometric mean is you basically, well, let's look at the original mean. When you talk about mean, median, and mode in statistics, when you have the mean of a certain set of numbers, you add them together and then divide by the number of terms. For the geometric mean, you multiply them together and then take your square root. That's it. So the geometric mean of A and B is you multiply them together and then take your square root. That's all we have to do. This explanation here, the whole thing, talks about when it's applicable. If you have a proportion that looks like this, you end up cross-multiplying, and you end up doing exactly this to solve for x. As an example, the geometric mean of 24 and 48. You're going to multiply 24 times 48, and then take the square root. Well, if we multiply 24 times 48, obviously we're going to get a slightly larger number than we're used to working with. It's 1,152. And then if we take the square root of that value, do this really quick here, we end up with a long, nasty decimal. It's about 33.9. I'm not so concerned with using a factor tree for a problem of this magnitude. We'll review factor trees and how we can simplify square roots further along in Chapter 7. I wouldn't mind if you left it as with the radical in it or as a rounded decimal to one decimal place. But in the next couple of problems, we'll take a look at when we actually can use a factor tree if you're interested in that. Let me see which one of these can work. All right, we'll do one of these and I'll make up one. So let's look at the first one, then I'm going to make up a problem. So if we're going to find the geometric mean of 12 and 27, we're going to take 12 times 27 and then take the square root. Well, if we do that, if we multiply these together, we should end up with 324. And then if we take the square root of 324, you should end up with a whole number of 18. So there are times that you will get whole numbers. Let's try one with a factor tree. Let's say we're taking the geometric mean of 8 and 4. So we'll multiply 8 times 4 and take the square root. Well, we end up with the square root of 32, which gives us a nasty decimal. So we don't like nasty decimals. So let's do a factor tree instead. Again, we talk about these in Chapter 7. So let's split this apart. We can split it apart into two factors. I know one factor we can do is 16, and the other would be 2. 16 times 2 gives us 32. But fortunately, the square root of 16 is a whole number. It's 4. And then the square root of 2 we tag on the end. So we can also write this as the square root of 2 instead of a nasty decimal. If you want a review in simplifying radicals, you can go to Khan Academy as well, and it could be helpful for you. We will talk about it in Chapter 7, most likely Section 1 or in between the end of Chapter 6 and the beginning of Chapter 7. So there's a brief video for you for Section 6.1. As usual, email me if you have any questions.